So last week we have studied left heaps and skew heaps, and there are different forms of priority queue. And today we're gonna continue to see yet another one, binomial queue. So again, the first question is, haven't we had enough about queues, priority queues? What is a binomial queue for? Why do we have to learn this? Well, say what is the average time for insertions with leftist or skew heaps? Do you still remember? There was a conclusion saying that the expected time complexity is yet an open question, but we have proved that it's bounded above, at least, it's bounded above by log n, right? So it's big O of log n. Although we expect this upper bound to be a little bit better than log n, but there's nothing wrong to say it's big O of log n because big O means an upper bound. So what's wrong with that? So what is the total time for inserting n keys into an empty binary heap? So according to the theorem given in our textbook, the total time should be linear. We have that built-in algorithm, right? So we can basically just put n elements into an array and takes a linear time and then call the function build heap and get it done in another linear time. So basically it's linear, it's big O of n. Then what is the average time? It's supposed to be a constant, right? We're making n insertions in big O of n time, and therefore, averagely speaking, it should be a constant. Therefore, a log n solution is not good enough. Okay, that's why we're introducing to you this new form of priority queue, binomial queues. It has a very special structure. It's not a tree, but a collection of trees. Say a binomial queue is not one heap-ordered tree, but rather a collection of heap-ordered trees known as a forest. Okay, and each heap-ordered tree is a binomial tree. So first of all, each tree has to be heap-ordered so that order property must be satisfied. So what is a binomial tree? Here's the definition. A binomial tree is defined recursively. We say starting from the smallest case, a binomial tree of height 0 is a one-node tree. A binomial tree of height k, if we denote it by b sub k, is formed by attaching a binomial tree b sub k minus 1 to the root of another binomial tree b sub k minus 1. So what does it mean? Let's take a look. Let's start from the smallest case, b sub 0. b sub 0 is a one-node tree. This is what b sub 0 looks like. Okay, now how about b sub 1? According to this definition, b sub 1 must be formed by attaching b sub 0 to the root of another b sub 0. That is, we have two b sub 0s, and we attach one to the root of the other one. Okay, so this is how b sub 1 looks like. All right, to give you more feelings, let's take a look at b sub 2. So what is b sub 2? We should have two b sub 1s, and we attach one to the root of the other one, and that is b sub 2. If that's still not clear enough, let's see b sub 3. So we're going to have two b sub 2s and attach one to the root of the other one. All right? So let's try to find some pattern here. This is observation, not discussion. All right? So b sub k consists of a root with how many children? How many? Just check this out. If this is 0, then it has no child. If this is 1, it has one child. If this is 2, this is 2. This is 3, this is 3. So if this is k, then the number of children must be k, right? What are those k subtrees? Just check b sub 3. The first subtree is b sub 0, right? And the second one is b sub 1, and the third one is b sub 2, right? So these k children are from b sub 0 to b sub k minus 1. All right, so b sub k has exactly how many nodes? How many? So how is b sub k formed? By merging two trees of the same size into one tree, right? So every time as k increases, the size will double. So we start from 2 to the power 0, which is 1. Next time we're going to get 2 nodes, and then 4 nodes, and then 8 nodes. So b sub k has exactly 2 to the power k nodes. Okay, now the last question is the hardest. The number of nodes at depth d must be what? With depth 0 we get 1. At depth 1 we get 3. And the next level another 3, and finally 1. What is the pattern here? Alright, the conclusion is that this number of nodes at depth d is given by a binomial coefficient. That's why we have this name for this special queue. Okay, it's called binomial queue because of this. The number of nodes at each level happen to be the binomial coefficient. In most of the Chinese textbooks, this binomial coefficient is denoted in another form. It's denoted by a capital C, right? And sub d, sub k, the smaller number at the top and the larger number at the bottom. Do you know what binomial coefficient is? Just to remind you, binomial coefficient is the coefficient of each term in the polynomial expansion of the function 1 plus x to the power n. Okay, and so this is the structure of a binomial queue. And we see that, okay, with that binomial tree structure plus the heap order, it means that each tree must satisfy the heap order property. Plus, it is restricted that there must be at most one binomial tree for each height. Okay, put all these three properties together, we conclude that a priority queue of any size can be uniquely represented by a collection of binomial trees. How come? Let's look at this example. Okay, let's try to represent a priority queue of size 13 by a collection of binomial trees. So where shall we get started? Well, think about a general binomial queue. It consists of several binomial trees, right? And at any position k, the number of nodes must be 2 to the power k. So it's like writing 13 as the sum of some 2 to the power of something, right? Does it sound familiar to you? The binary numbers, right? It's like to rewrite 13 in its binary form, right? So each one corresponds to 2 to the power of something. And if there's a 0, it means that this term doesn't exist. Okay, so it corresponds to what? It corresponds to a forest like this. That means b sub 1 doesn't exist. Okay, since we have 1 at 0's position, we have b sub 0. And therefore we have 1. Okay, and the second bit is 0, which means we don't have b sub 1. This tree is absent. We have 1 and 1 corresponding to 2 squared and 2 cubed. And therefore we have b sub 2 and b sub 3. So the total number of nodes can be calculated this way, which is equal to 13. So you can see that the form of this forest is closely related to the binary form of an integer. And since for each integer it has a unique binary form, therefore we have this conclusion that the priority queue of any size, that's any integer, can be uniquely represented by a collection of binomial trees, so by a binary number. So when we fill in those key values, we have to make sure that each tree is, in this case, a min heap.